All right, welcome back. So today we are going to look at an application of integration, sort of asking a different question of a function. Rather than asking what is the signed area between the function's graph and the horizontal axis, we're going to ask what is the length of the arc along the graph of f of x on the interval ab. That's to say, if you were sort of setting a piece of string on top of this function, how long would that string have to be so that it would set directly on top of that function's graph and extend exactly from where the function is at A to where the function is at B? And so sort of how long is this curvy bit of the function's graph? And I mean, it's a reasonable question. And how are we going to approach this? Well, we're going to approach this in the manner that we've approached integration when dealing with applications other than just signed area previously, which is to say, we're going to take our interval of interest and chop it into bite-sized pieces. And on each of those pieces, instead of considering sort of the curvaceous region defined by the function itself, we're going to essentially break into linear pieces. So we're going to break into straight line segments. And this may be kind of tricky to visualize when I'm drawing this directly on top of the function's graph. But if I draw over here sort of what we're looking at, we've got these distinct linear pieces that ultimately result whenever we write this out. Okay, that part is not worth our time. So, okay, we've got these distinct linear pieces. And now what are we going to do with these distinct linear pieces? Well, if we can deduce the length of one of these pieces in general, then we can integrate that expression over the region of interest, and that's going to give us the length of the arc. Because, I mean, in principle, integration is going to be chopping into a bunch of tiny pieces, and if we chop into a bunch of tiny pieces, our approximation is going to have practically zero error. And so let's start by computing the length of one piece of our linear approximation. And so what we're looking at here, take any piece, maybe a piece that looks like so, we're going to try to compute the length of this piece. So how long is this single segment of a linear approximation of our function's graph? Well, we can actually begin to deduce some measures about this length if we think, well, hey, horizontally, we actually know how far this piece extends horizontally, because conventionally, when we break our interval from A to B into a bunch of tiny pieces, each piece is of width delta x. Which subsequently means, actually, the vertical portion here, depending upon what our function's expression is, will be some corresponding delta y. And now, since we have a horizontal measure delta x and a vertical measure delta y, since horizontal and vertical meet at 90-degree angles, hey, we've got a right triangle here, and we have a Pythagorean relationship, delta x squared plus delta y squared equals L squared. And what are we trying to solve for? We're trying to solve for the length of one piece of our linear approximation. And so, well, the length of that one piece is just going to be solving for L. But we can solve for L here by taking a square root. Now, when we do so, you might say, but oh boy, how is that functional expression going to be integrable? Well, here's a little sort of tactic we can employ, because we want a delta x really like hanging out on the right of our expression so that it would be like the dx within our integral. Well, we could get a delta x hanging out on the right of our expression if we just factored out a delta x squared from our square root. So let's factor out a delta x squared from our square root so that that delta x squared would simplify to just be delta x. Well, if we factored a delta x squared from the square root, that first term would just become 1, and that second term would be delta y squared divided by delta x squared. Because if you divide away a delta x squared from something that doesn't have a delta x squared in it, then you're going to have a delta x squared in the denominator. If I rewrite what's in this square root nicely in the simplified form, where we've taken the square root of delta x squared and simplified it to just be delta x, we end up with 1 plus, let me just write it as delta y over delta x squared. And why this is particularly nice is, well, we've actually got a form of our derivative hanging out there within our square root, inside that square for that matter. But notably, with what we were trying to do, we were trying to find the length of one piece, because now that we know the length of one piece of this linear approximation, we could integrate over our interval of interest namely the interval from a to b, and sort of take the question out of the situation and have an exact result for our integral of interest. We're going to have an integral from a to b, because that's the region of our function for which we're trying to deduce the arc length. The expression now, we got to be careful, because instead of using deltas, we're integrating, so we're going to use d's. So we've got 1 over dy over dx, that's just our derivative, squared, and then we've got the delta x hanging out on the right, which looks just like an integral should. We've got the dx hanging out on the right, and then we've got this functional expression. So let me pause, clean the slate, and then we'll work through an example to put this formula to use. All right, so let's work out this example to apply the arc length formula that we just produced to find the arc length of the function f of x equals x to the 3/2 power on the interval from 4/3 to 20/3. So let's have at it here. So to apply our formulation, we're doing an integral in this case from 4/3 to 20/3, kind of nasty bounds, but we'll see how this plays out in the long run. Inside our integral, we've got a square root expression, 1 plus, well, dy over dx squared. Hey, that means we're going to have to compute our derivative here, which means take our f of x, maybe let me write it up here. What's our derivative? I tell you, I'll use the exact form that we've got in our formula, dy over dx. Hey, it's just the power rule, right? Bring the power in front and reduce the power by 1, but 1 less than 3/2 is 1/2, 2/2 less than 3/2. And so there's our derivative that we need to apply into our formulation. So the derivative squared would just be 3/2 x to the 1/2 quantity squared, and then we've got the dx hanging out on the right, as we would expect with an integral for a function of x. Now, we've got to square what's here. Now, just to be clear, we got to square the 3/2 as well as the x to the 1/2. Now, fortunately, the x to the 1/2 works really nicely, because a square root squared is just x. The 3/2 squared is only so complicated, it's 9/4. So, okay, if we can just integrate the square root of 1 plus 9/4 x, if we could just find the capital F function in this setting, then we'd be in business. But, well, we could do that by using u substitution, because check it out. If we let u be the inside function here, let me grab another pen to make this apparent. Let's see, we got 1 over 9/4 x. That could be our u, and if that was our u, then what? Du over dx would be equal to just 9/4, which would mean within the context of this situation, dx would be just, let's see, 4/9 du. And so what are we going to do? We're going to take the dx and replace it with 4/9 du, and we're going to take what's inside our square root and write it as u. Now, we got to be conscientious, because we're using a definite integral here. Our original bounds are in terms of x. And so we're going to have to take our original bounds and write them in terms of u in order to get a new integral in terms of u. So looking at our bounds here, we can use the u equals something in terms of x to evaluate it x equals 4/3 and evaluate it x equals 20/3. Okay, x equals 4/3. We would get 1 plus 9/4 times 4/3, which when we cancel it out, the 4's cancel, the 3 and the 9's, that's 1 plus 3. That just gives us 4. What about 1 plus 9/4 times 20/3? Okay, that might be slightly more annoying, but we can still do it. The 1 and the 3 cancel to be 3. The 4 and the 20 cancel to be 5. We have 1 plus 3 times 5, which is 1 plus 15, which is 16. Okay, so be it. In our new integral in terms of u, we would have downstairs u equals 4, upstairs u equals 16, and then, well, hey, we just have the square root of u, right? That's only so bad. That's u to the 1/2. And then we have that 4/9, I'll bring that out in front. That's just a constant multiple, and then our du, which ultimately means, well, u substitution gave us something that is pretty straightforward to integrate. We got to use the power rule, so we got to increase the power by 1 to 3/2, put a 2/3 out in front, so we'll have the 4/9 all the way out in front. Then we'll have the 2/3 u to the 3/2 evaluated between 4 and 16. Now, it might be nice to take that 2/3 and bring that to the outside as well. And so if we bring the 2/3 to the outside as well, that's 8/27 by my count. And then what do we have? We're going to have 16, because we got to evaluate at the top bound, right? 16 to the 3/2 minus 4 to the 3/2. And looking here, anytime you evaluate a fractional power, right, the denominator is the root, the numerator is the repeated multiplication. So the square root of 16 is 4. 4 times itself 3 times would be 64. The square root of 4 in this case would be 2, and then 2 times itself 3 times over would be 8. So we have 64 minus 8. Let's see, 64 minus 8 is 56, right? So whatever this comes out to be, this is kind of a nasty number, but it is what it is. The result here, let's see, again, this was 56. So let me just write it as 56 times 8 divided by 24. I realize that's probably able to be simplified, but this example actually echoes something about arc length, which is the idea behind arc length might be the most important thing. Whenever you actually get into computations, the computations get pretty nasty pretty quick, because this actually isn't that crazy of a function to deal with. And well, hey, the computation became what it was. So whatever this fraction simplifies to be, so be it. At least we have now deduced how long this function's arc is if we set a piece of string on it between 4/3 and 20/3, which is, you know, hey, a pretty cool thing to have computed. And hey, it at least shows that the arc length formula can give us some interesting results.